So it's very bright up here. I can barely see you. I'm really excited to be here today. I hope you are too. I hope everyone's learning a lot today. Before I get started, I'd like to take just a moment to thank the Next event staff. We can't do things like this without them. So let's all give a real quick round of applause for the folks that have made this possible for us. Thanks, that's awesome. So the other thing I'd like to do before I get started, I'd like to remind you to provide feedback for all the sessions that you've attended today, including this one. And we use that feedback to ensure that future topics are relevant, high quality, and compelling. So please do take the time to let us know how you feel about the content. Real quick about myself, my name's Jeremy Johnson. I'm a product manager with Google Cloud. I specifically work on networking. My primary focus in product management is around IP addressing, and we are actually doing a panel on IP addressing tomorrow, so please come at 9 a.m. tomorrow and listen to IP addressing talk as well. I think one of the things, I've been at Google for about a year and a half, and one of the things that's really awesome about working at Google is working with world-class engineers. I mean, I've worked with some great engineers over my career. I've been doing this for about 25 years, and I've really honestly never worked with such a great group of people. And it's my honor today to present some of the work that they've done to create what I consider probably the greatest network on the planet. And hopefully I can do that justice. So our goals today are really simple. We're going to go over our global network, which if you've been following the operations track, you've probably heard a lot about over the last couple of days. You're going to hear more about it today. We're also going to talk about the Andromeda Architecture, which is our software-defined network that operates our cloud. It's not the only software-defined network that we run, but it's the one we're talking about today. And then finally, throughout the slides, I'm hoping to get across some of the practical benefits of the architecture and infrastructure that we've put together. So this slide probably looks familiar to some folks, and I hope it does. But we think this is really important. This is a view of our global network, and it's important to think about when you think about Google's cloud. It's important to think about the global network. The reason for that is that everything we do centers around this thing, this global interconnected network that we've built, and we're pretty proud of it. Some numbers for you. We've got 20 cloud regions. I think if you were here last year, that number was significantly smaller. I think it was in the single digits last year. So we've been expanding really fast. Yeah, 125 POPs. The POPs are where we connect to the internet and also provide edge network services. Of those 125 POPs, 90 of them serve as CDN locations. 72 of them serve as dedicated interconnect locations. We've got 15 Google data centers, so not every region has its own data center. That might be a little bit confusing, but trust me. We've also got 26 renewable energy project locations, hundreds of thousands of miles of fiber optic cable, and 13 subsea cable investments. So we've put a lot into this infrastructure to make what we, again, think is probably the best network on the planet. So the question, I guess, is, why does this really matter? And to me, it comes down to two things. It's less work for y'all, and it also provides more options. And what do I mean by less work? When we think about things globally and we offer you global constructs, you're able to do things like create one VPC globally without replicating it across multiple regions and then having to worry about replicating configuration and connectivity across all those regions and replicating all of your policies across all of those regions. For us, it's one global VPC, and we've created things like the shared VPC and host projects so that you can really leverage that. We'll talk more about that in a minute. Also, we've created a whole bunch of services that work both at the global level and at the regional level. So for example, some of our global services are things like the Layer 7 Global Anycast VIPs. This provides the ability to do load balancing at a global level without having to play games with DNS, et cetera. We've got many interconnect locations across the globe. We also have differentiated network tiers. We've got what we call a premium tier and a standard tier. Actually, we've got a booth outside that shows kind of really what's going on there. But the difference between the network tiers is really simple. The premium tiers leverages the entire global network. So your traffic can enter our network anywhere, and it can exit anywhere in the network. The regional services, or the standard network tier, allows traffic to enter in a regional location or someplace approximately close to a region, so the POP's nearby a region, and also that allows traffic to only exit those places. And these are choices that you might make based on cost. You might make them based on local rules or compliance purposes. So again, this is really interesting and compelling from my perspective, because you've got more choices, I think, with our network and our cloud, specifically when it comes to networking, than any other cloud. So I'm sure you've all seen that slide before of the global network. So I kind of wanted to give you an idea of what really goes into that. And so what we've got here is a picture of one of the fiber ducts out, or actually a fiber trench, and several dozen fiber ducts outside one of our data center campuses. And the thing that's interesting about this is that each one of those orange pipes has thousands of strands of fiber just for that one campus. And also, we've got hundreds of thousands of miles of global fiber backbone. One of the things that's interesting about this backbone is there's so much redundancy built into it that we can lose many connections and still achieve global reachability. So again, this is also the infrastructure that powers Google. So I think you're all well aware of our commitment to to reliability at Google, and I think it probably is obvious how much of a problem it would be if we lost connectivity. So this is a major part of our story. So I'm gonna take the time now to talk about some network functions. And the way we're going to organize this is I'm going to talk about these network functions at a somewhat high level, and then we're going to dig down deeper into them and talk about how we actually make those things happen. So it all starts with this global VPC. The idea of a global VPC is that we can have multiple clients running on the same network using overlapping network namespaces. We all use 10.0 for something, but they're all sharing the same network infrastructure, right? So this requires us to build functional and performance isolation for all of our clients. Oops, I should be using that. I don't know what slide I'm on now. I apologize. So network functions, we talked a little bit about the global load balancer. I want to talk about it a little bit more. So with a global network, we're able to provide, at those POP locations, we're able to provide load balancers that present a single global IP to all of your clients across the world. So one VIP with the same IP address serving the entire globe. And the way that we're able to do that is we leverage a technology called Anycast, which really means that we're advertising the same IP addresses at all of our locations, and we've IP'd your VIP with that same IP address at each one of those locations. What this does is it attracts traffic from our peers to the most geographically proximate ingress location, and then from there we backhaul that to whatever cloud backend you have serving it. This enables you to do global load balancing, again, without manipulating DNS or in fact taking sometimes signals from DNS that are potentially inaccurate. So this slide's a bit of a mess, so I'm going to try and walk you through it. What we have here, this is an engineering conversation, right? You weren't expecting really beautiful slides, were you? So anyway, we're going to start from, I guess, your right side and walk it towards me. So what we've got here is a basic example of a VPN using our global network. And again, this is about choice and ease of use. So let's say you've got your on-prem network and you've got this green VPN termination device at your end. You're going to traverse the internet with your IPsec tunnel and you're going to land that at a VPN gateway in a cloud region, right? So when it lands in that cloud region, you've got some choices. You can first of all, just use resources in that cloud region and route back to that VPN termination point through that tunnel. Or you can export the routes using our cloud router and also a toggle called global routes to route all the information that your project learns from the VPN globally. And that's just a simple toggle. So you can either isolate your VPN endpoint locally, or you can enable it globally. Likewise, you can advertise your routes from Google that you learned from Google back across that VPN connection, including any routes that your VPC has globally. And you do that with a mechanism called custom routes. And this is just a small example. Also, I've got in there a layer 4 ILB. The interesting thing about that is that you can literally use an internal load balancer at the far end of a VPN connection to load balance internal traffic, again, anywhere in the world. And we're going to talk a little bit more about how that works in a minute. So the network load balancer is interesting. This is more of a regional construct. But the interesting thing about the network load balancer is it actually uses our edge pops as well, because this is for public internet traffic coming into a cloud region. But it's not load balanced at layer 7. So when we talk about the global load balancer, the layer 7 VIP, that does termination. So it actually terminates an HTTPS connection, it terminates an SSL connection, or it proxies TCP. This is actually a layer 3, layer 4 load balancer that directs traffic to backends in a cloud region, a specific cloud region. So if you wanted to load balance across multiple regions, in this case, you would actually deploy load balancers in each region that you wanted to load balance. And so in this situation, we've got Maya in California, Bob in London, and Shen in Singapore. And a couple of the interesting things about this load balancing capability is that we do preserve the client IP address so that we can do direct server return. And also, it facilitates creating firewall rules on the cloud backends. This is kind of important, again, to make things easy. You have the same IP address on your LB VIP as you do on your backend VIP. And so it's just one firewall rule at the regional level to manage security for those connections. Another regional function, this one's more truly regional, is the internal load balancer. We talked about it a little bit in the case of the VPN, but sort of how it works is, again, it allows you to create an internal VIP, but in this case, it's completely programmed in a distributed fashion across our Andromeda infrastructure. There are no middle boxes in this case. In the other cases, the global load balancer, there's a middle box that's doing termination. In the network load balancer case, there's a middle box that's actually directing traffic at the edge. That's something we call a maglev. Internally, in these internal load balancers, this is completely using the distributed software-defined network that we've built. And it's actually programming flows directly onto each host. And there are no middle boxes to speak of. Again, client IP addresses are preserved. It's easy to set. It's easy to control access with firewall rules. And we believe it offers higher performance because of no choke points. Again, no middle boxes for these kinds of load balancers. So let's talk a little bit about how it works. So again, we talked about that global VPC. So remember, we've got to do functional and performance isolation. And what that means is, again, every project in cloud is using the same infrastructure globally, but you're all operating on different or distinct isolated network namespaces. So we all have overlapping IP addresses, basically. But you're also all expecting us to provide performance guarantees. And so we also have to do isolation at the performance level. And then finally, we have to offer high availability to everyone. So our high availability targets, and this is interesting, we use a mnemonic called 345. So if you deploy an application in a single zone, our target for availability is 3 nines of availability. If you deploy across 2 zones in the same region, or regionally as we would call it, then you would expect 4 nines of availability. And if you deploy something globally across multiple regions, you should expect 5 nines of availability on our network. We think, number one, that's unique, but number two, that creates a whole bunch of problems for us. Since if your application availability needs to be 3, 4, 5, that means that what we're deploying is actually 4, 5, 6. So a unified view of functions, this is where I go to the note cards. So bear with me for 1 second. So where are we? OK, so we wanted to spend some time on the data plane. And basically, the idea, the message behind this slide is that we've built the core network functions into the VM hosts themselves. And that's a consistent theme across the Andromeda network. There's a constant evolution of features that we push out weekly. And we can do this because we support live migration so that we can do host maintenance in a non-disruptive fashion. And also, we can do hitless upgrades of our data plane. And we'll talk a little bit about how we can do that as well. So the architecture itself, first of all, is replicated across regions. It's sharded across regions. And it's also sharded across zones. So what we've done is we've basically built a hierarchy of a control plane that manages a data plane. So the first up at the top, and you're not going to see it in this slide, is the Cloud Cluster Manager. This performs a lot of tasks, including configuring storage. It also configures compute and networking. Below that sits the Fabric Manager, which is a regional level control plane. And that comprises a high-level API to configure virtual networks and other functions. And then you get down to the OFE, which is our OpenFlow layer, which takes our API abstractions and then converts those into OpenFlow configurations and programs those constructs directly to the switching layer. And then the switching layer itself is a programmable software switch based on Open vSwitch, and that's the core data plane for data processing. So, as an example of how this works. Again, we talked about internal load balancers. So this slide here is about how we separate, first of all, the control plane and the data plane. So the VMC and the OFEs are where the control plane happens, and those program the data plane. So in this case, what we've got is control messages being exchanged between the client VM and the CFEs, and also with the VM controllers and the Cluster Fabric Manager. We've got stats for health reporting, and we've also got health checks happening on the other end for load balancing high availability. And then finally, you've got VM to VM traffic. Something to point out here again is typical load balancers have middle boxes, but our approach for the ILB, as I described before, is that we built the load balancers as distributed services. So what's happening is these health checks are actually checking services on backends across multiple backends, and the client VM in this case is where the load balancer itself is running, and we're programming paths to those backends directly into each of the hosts, right? Both forward and reverse. So then we can also extend those functions. And I think the interesting thing about this is we can extend those functions without changing topologies. Because again, we don't have middle boxes, so all we have to do is configure the control plane so that we can update the data plane to add that new function into a path. So if we add an on-prem situation in a VPN, it's very simple for us to then program the flow to the VPN termination point. That programs the backends that allow the load balancer to connect to those backend VPNs. Again, we didn't change any topology. This was simply a software-driven operation. Okay, so let's talk about network programming models. So it's interesting when you're doing a software defined network, you have to program all of these flows. You're not using distributed routing technologies to enable every device to talk to any other device. You're not using ARP, for example, to say, okay, who has this IP address? We actually have to install flows for every single conversation that could possibly happen. So when we started by configuring full mesh communications. And that works really well for small networks, but it starts to get really ugly for big networks, and that's what this is showing. This is actually a quadratic scaling problem, and in order to solve this, we had to do something different. So what we did is we came up with a concept called hoverboards. Basically, hoverboards are a software gateway. We use this to program simple paths from every VM through that software gateway to any other VM. So rather than having a full mesh, you traverse the hoverboard, and we still pre-program small networks. So small networks still have a full mesh. Large networks have hoverboards, and all those packets go through the hoverboards. And then if the flows get too heavy, in other words, if the hoverboards reach any scaling constraints, we just offload those. We actually program a direct flow into the client or the two hosts that need to talk to each other. So by doing that, this software gateway allowed us to achieve some really staggering scaling improvements. And what we found out, and one of the design questions that we had to ask ourselves when we built those hoverboards, is actually, is this going to hurt by putting these middle boxes in between all of this? So we get a scaling benefit from the configuration and control plane, but are we going to suffer on the data plane? And it turns out that the vast majority of hosts never talk to each other. And then the vast majority of hosts that actually do talk to each other are very, very quiet. We're talking less than 100 kilobits per second. And so basically, we have a threshold that says, hey, anything that's got a larger flow than this, we'll just offload that to the host. So oftentimes we get questions. So how can I ensure that my hosts will directly talk to each other if I have a latency-sensitive application? It's really simple. Send a lot of traffic. So there we go. So again, we were able to reduce the programming time by implementing the hoverboards. We were able to improve programming times by a factor of 37x. So that was a really, really important achievement to scale this network to the millions of users that we now have. We also found that we could use hoverboards to scale not just between VMs, but also between zones. And so we just took it to the next level and said, okay, well, if we've got hoverboards inside the region between VMs, we also know that, okay, the communications between two hosts on different zones is also likely to be quiet. And it turns out that that's also the case. So what we did is we also inserted hoverboards between zones. And so again, two hosts, one in each different zone in the same region. The low bandwidth routes traverse the hoverboards. We do local stats. This is also an interesting detail of the hoverboards. You might think that the hoverboard itself is actually measuring the size of the bandwidth between the two hosts, but it's actually stats that are driven from the host itself, and that's to prevent the hoverboard from right at the moment when it actually is suffering or needs more resources. We're not trying to make it more busy. We can actually just offload that to the host itself, and the host itself can create its own flows. And this is another benefit of distributing our network functions across the hosts themselves. So when we see those stats and the bandwidth is high, we just go straight host to host. So again, this works just like inside of a zone. It's just one more hierarchy of hoverboard. So I'm going to switch gears here now and talk about the way that we do networking at the host level. And one of the things that people may find odd or at least unique about us is that we do all of our networking on the host level in user space. And so kind of first of all, why do we do this in software? And we'll get to the reasons why we do this in user space. But the primary reason is we're able to get native hardware performance in software. Our fast path, which is basically just doing packet forwarding, is able to push 3 million packets per second with one dedicated CPU per host. And that translates to greater than 30 gigabits per second on ideal situations. Then we also use coprocessors for CPU-intensive functions like denial of service protection, IP rewrites, et cetera. We'll talk more about that in a second. And then we also have an on-host control plane. And with an on-host control plane, we're able to do things like live migrations and hitless upgrades because we can just swap out the data plane right underneath that control plane without losing any state. So again, why build in user space? Well, there are a lot of advantages. First of all, there's security advantages. It runs without root, so pretty much the entire data plane has no privileges. And secondly, we can do things like continuous fuzzing because the code footprint is so small. We can also do things like address space randomization. It also improves robustness. So unlike a kernel bug, which could take take down a whole machine, a user process can go down and come right back. And likewise, user space processes allow for nearly weekly upgrades via our hitless upgrade process. Live migrations, again, also allow for VMs to be migrated between physical hosts without disruption, enabling transparent host maintenance. So it also provides a flexible architecture. So our data plane is fully programmable. The control plane basically programs OpenFlow rules and the data plane itself. It's pretty simple. The example on this slide, we have 3 tables, incap, decap, and maybe some special functions. This all programs the data plane, which is a key action-based data plane. And we've also enhanced the overall vSwitch layer to include things like stateful load balancing, which aren't available in your standard implementation of vSwitch-D. It also does different features for us. We've created custom features for ourselves like stats and billing, and we also have the ability to do policy enforcement. These network functions are also applied directly into the data plane via coprocessors. So again, coprocessors outside of the fast path, which again, the fast path is primarily just doing forwarding. These functions outside the fast path include things like traffic shaping, denial of service protection, abuse protection, IP address rewrites. So for example, when you're trying to send packets to the internet, you have to do a rewrite from that private IP address to a public IP address. All that happens in the coprocessor. So a little bit of history about our CPU efficiency gains as we've improved Andromeda. First of all, when we built this stuff, it became very, very evident that we needed to minimize the host and guest network CPU cycles per byte. And the way that we did that was, over time, moving off of the guest completely, off of the host completely, and bypassing as much of the guest as possible. So in the Andromeda 1.0 implementation, there was a kernel Open vSwitch, and the Open vSwitch control plane on top, and then a hypervisor. The kernel data path only had support for egress data offload, but it didn't have support for ingress data offload. As a consequence, you can see that resulted in a lot of host CPU cycles. Andromeda 1.5 optimized the host data path. It added ingress for offload support. It added ingress offload support, but still maintained a kernel data path. This optimization, along with the introduction of receive offload support, improved both the guest and the host CPU performance, and it also allowed for live migrations, which was a pretty big deal. We couldn't do that before we had ingress support. But the real big evolution came with Andromeda 2.0. There, the entire data plane was moved into user space, but we still required one thread of handoff. So there was still a software virtual NIC that we had to talk to And so there was a context switch. But as you can see, there was still a significant reduction in cycles per byte. With 2.1, we removed that one thread handoff. And with 2.2, we've added support for memory copy offloads. And that's led to a decrease in more than 50 cycles per byte since we started with Andromeda 1.0. So some throughput numbers. On a single core per host data plane, again, the FastPath uses one dedicated CPU on each host. On one single core per host for our data plane on Skylake testbed hosts, both hosts connected to the same top of rack switch, we're able to get 38 gigabits per second throughput. Again, this is ideal situation scenarios. We don't support 38 gigabits per second in VMs. All right, you're laughing. I have something for you. So anyway, so we also noticed some VM to VM round trip time latency. So again, with the single core per host and in the same top of rack switch on Skylake infrastructure, we had normal TCP round trip time in the order of 25 milliseconds. With our TCP busy polling, so we're not doing interrupt-driven networking anymore, we were able to lower that down to 15 milliseconds. And with DPDK, we're able to lower that below 10 milliseconds. All right, so a quick summary. So what we talked about today, global network. Why is a global network important? It's easier to deploy. You've got fewer things to do. It's more reliable. The infrastructure that we built is heavily redundant. It's more flexible. You have the ability to operate functions both globally and locally. We talked about Andromeda. The key principles between Andromeda are isolation, performance, and agility. So isolation, again, we've got performance and functional isolation. We have to keep all of these network namespaces distinct. And agility, we need to be able to improve as we build, right? And so this agility that we've built into this allows us to do weekly upgrades. And then finally, some network functions. And by the way, this is by no means complete. Uh-oh. I gave away the ghost. Anyway, these network functions are by no means the comprehensive list. Hopefully, you've been spending some time with this, and you know that there are many global network functions. There are many regional network functions. We only talked about a few. And then I have one more thing for those that were snickering a little bit. We are announcing today that we support 32 gigabit per second networking, host to host. The way that we talk about networking in our cloud is a general rule of thumb is that you get about 2 gigabits per second per vCPU. So up until today, that scaled up to 16 gigabits per second. So you on an 8 CPU or an 8 vCPU box, you could get 16 gigabits per second. Now this requires the Skylake platform. However, with a 16 CPU Skylake platform, you can get up to 32 gigabits per second. It requires zero configuration. There's no SRIOV required. No different drivers. You can use the standard VirtIO driver, and this will just work. With that, I'd like to invite you to go to the rest of our networking conferences or our networking breakouts for the rest of the week. There's an interesting hybrid one tomorrow that one of my colleagues is giving, and there's also again 9 a.m. tomorrow. We have an IP addressing in the cloud panel, which I think, I'm a nerd, but I think this is a really cool topic. And then if you want a cloud poster, go to g.co/poster, and you can download one, or we'll ship it to you. All right, we're done.